Good morning. Welcome to the third of our lockdown webinars. I hope everyone's keeping safe and well. My name's Keira Proctor and I'm the Managing Director for the A. Proctor Group Limited. And today we're going to be taking a look at the fundamental physics which affect our buildings. As always, we'll be having a Q&A session after our main presentation, so if you have any questions you can type them into the chat box, or if you prefer email them to webinar@proctorgroup.com. Or you can also send us a Twitter @ProctorGroup. Here at Proctor's, we focused for a long time on the importance of good design to manage the movement of heat, air and moisture around the building envelope. So today's webinar looks at some of these interactions and how we can best manage them. In order to design structures that are energy efficient and healthy to live and work in, designers have a clear need to balance the heat, air and moisture movement throughout the building envelope. So, understanding these elements and how the interactions between them work is an increasingly important factor in ensuring today's highly optimised buildings are fit for purpose, not just today, but for many years in the future. So to begin, let's review the basic factors relating to heat, air and moisture movement, starting with heat transfer. In terms of energy performance, managing heat transfer is the most obvious consideration in our design process. There are three basic models of heat transfer that are present in all buildings to some extent: conduction, convection and radiation. The simplest way to illustrate all three is heating a pan of water on a hob. Conduction. Conduction happens where two objects are in contact with each other, like the base of the pan sitting on the hot plate. This direct contact lets the heat flow from the warmer hot plate to the colder pan, either until the temperatures equalise or the pan is removed. Most building insulation boards, such as mineral fibre, polyurethane, for example, work to resist heat transfer by conduction. Convection. Convection occurs when heat is transferred by a fluid medium, which in buildings is usually air, but in our example here is the water in the pan. As the water at the bottom of the pan heats up, its density reduces and the warmer water will rise relative to the surrounding cooler water. The cooler water then sinks to take its place, setting up a circulation of water known as a convection current. As the temperature of the water becomes more uniform, the speed of current will reduce. In buildings, convective heat transfer can be minimised by ensuring good air tightness is achieved, restricting this circulation from happening. Radiation. Radiation is the transfer of heat from one material to another, which occurs by means of electromagnetic waves. Radiation does not require either physical contact with the materials or a fluid medium. A warm surface such as our hot plate will emit infrared radiation, which can travel across a space, even in a vacuum. When these infrared waves strike another object, they are converted back to heat. The efficiency of this conversion process is governed by a property called surface emissivity. The lower this value, the less able a material is to absorb or emit heat via radiation. In construction, reflective foil membranes and foil-faced insulation materials can help limit heat transfer by radiation. So those are the basic mechanisms of heat transfer, but now let's move on to the specific properties materials have and how they influence the design choices we make. The most relevant material properties to our discussion today are thermal conductivity, thermal resistance, thermal mass and thermal transmittance. Thermal conductivity. The thermal conductivity, also known as the lambda value, or K factor, is measured in watts per metre Kelvin and tells us how well a material lets heat flow through it at a given temperature. The lower the conductivity, the better the material will restrict heat losses. In our example here, you can see that the high thermal conductivity steel beam on the left quickly transfers heat from the burner. This is because steel has a relatively high conductivity at about 50 watts per metre Kelvin. On the other hand, in the concrete beam on the right, it takes a lot longer for the heat to reach the top side of the beam. The K value of concrete is much lower at around 1 watt per metre Kelvin. Materials commonly used as insulation are lower still, typically in the range of 0.015 to 0.044 watts per metre Kelvin. Thermal conductivity is useful for comparing materials as it does not account for thickness, making a straight comparison of how good is the insulation easier. It's less useful, however, when we need to consider a specific application, such as roof or wall, as it doesn't account for how much material we're using. If we want to include thickness as a factor, we need to look at the thermal resistance, or R value. This is measured in meters squared Kelvin per watt and is calculated by dividing the thickness of a material in meters by its thermal conductivity. For a given material, the thicker a block we use, the higher the R value will be, and therefore the greater its insulating effect. Thermal resistance is directly proportional to thickness, so looking at the two blocks of concrete shown here, if we halve the thickness of the block, we will double the rate of heat flow through it. Thermal mass. As well as how materials respond to heat flow, their capacity to retain heat is also important. This is governed by their thermal mass, also referred to as fabric heat storage. We can see here how the low thermal mass steam beam cools down quicker than the high thermal mass concrete. In buildings, this property can be used to even out temperature swings and maintain a consistent temperature with less heating or cooling energy input. The final property we need to consider here is the thermal transmittance, or U value. The U value of an element is the inverse of the sum of all the R values in a construction and gives an indication of the heat flow through a given element, in this case a wall. In practice though, the R values for each layer need to be adjusted to reflect things like air gaps and structural elements like studwork. Locations where structural elements intersect insulation are known as thermal bridges, and in these areas heat typically flows faster than through the insulation. U values are therefore adjusted to reflect this, and the methods for doing this are given in the ISO 6946 standard and the BRE guidance document BR 443. Non-repeating thermal bridges, such as floor and roof junctions and corners, are also adjusted for. The heat losses associated with these features are called psi values. Where these bridges occur, the temperature in the element will be lower, and if they are not properly designed, cold spots can occur internally, which can lead to condensation problems, both on the surface and internally. If and where condensation will occur in an element can be predicted by looking at the dew point temperature. We can use the R values for the layers in the element to produce a temperature gradient graph. From this graph, we can then use a combination of the internal and external environmental conditions and the vapour and thermal resistances of the layers within the construction to produce a corresponding dew point graph. Provided the actual temperature gradient through the structure remains above this dew point line, no condensation will form. However, if the dew point and temperature gradient graph lines intersect at any point, then condensation will occur. We'll come back to condensation and other moisture sources later on, but for now, let's consider air movement in structures. It's important here to note that what we're talking about is unplanned air movement. Planned air movement, provided by ventilation systems, is an important part of maintaining good indoor air quality. So when we talk about air tightness, we really mean unintentional air openings and the uncontrolled exchange of air from outside to inside and vice versa. This can have a significant impact on the overall energy efficiency of a building, and as fabric insulation levels increase, this becomes an increasingly influential factor. The two basic factors affecting air movement are infiltration and exfiltration, air moving in and air moving out of the envelope, and there are various mechanisms which drive this. The three main air pressure phenomena affecting air movement are stack pressure, wind pressure, and mechanical pressure. Stack pressure. The first, stack pressure, arises from the stack effect in the building. This is an important driving force behind passive ventilation strategies. However, if not properly designed for, it can lead to air leakage problems. Stack pressure is caused by the convection current we discussed earlier, where warmer air rising through the building draws cold air in at lower levels. This creates pressure gradients as shown, from outside to inside at the lower levels and from inside to outside higher up. This effect becomes more pronounced the taller the building gets. Wind pressure. The second, wind pressure, results from a difference in pressure between the windward and leeward sides of the building. The positive pressure on the upwind side pushes from outside to in, and the negative pressure downwind draws internal air outwards. Being driven by weather, the directionality and extent of this pressure can vary considerably. We also have to consider the effects of shelter provided by surrounding structures and any variations that may occur between the upper and lower stories of a building. Mechanical pressure. The final air pressure driver is mechanical pressure, associated with ventilation and air conditioning systems. In high-rise residential and commercial structures, large-scale air handling equipment is capable of creating substantial pressure drops within the building. Natural sources produce pressures of up to 10 pascals, while mechanical systems can go as high as 60 pascals. If this is not managed correctly, it can contribute by drawing air into the building envelope from unintended sources. Additionally, if the system is not installed well, leaking ductwork may draw air into the system that has not been accounted for, with a corresponding detrimental effect on the efficiency of both the system and the building as a whole. So the common factor across all these mechanisms is the presence of holes in the building envelope, through which uncontrolled air movement can occur. This air movement can not only significantly reduce the energy performance of the building, but introduces a discrepancy between the as-designed and as-built performance that can lead to complex and expensive remedial action. It's therefore important to ensure that the air barrier system used is robust and flexible enough to perform as designed, both initially and throughout the building's life. Traditionally, air barrier membranes have been installed internally on the warm side of the insulation. Typically, these also function as vapour control layers. This positioning requires the air barrier to be sealed at all surface and structural penetrations and remain sealed. If the membrane is damaged either during installation or following trades at later refurbishments, for example, then both air leakage and moisture vapour ingress problems can arise. If care is not taken to seal all external elements effectively, this can also allow cold air movement around insulation, known as thermal bypass or wind washing, which can lead to reduced energy performance, cold spots and condensation issues, particularly if there are continuity issues with the airtight VCL line. By moving the air barrier to the cold side of the insulation, external systems such as our wrap-tight allow for an almost penetration-free airtight layer, which can be installed faster and more robustly. Far simpler than internal options, the wrap-tight external air barrier system maintains the envelope's integrity with less building services and structural penetrations to be sealed and less room for error. Being fully self-adhered to a substrate is also better able to resist external forces, such as wind loads, ensuring good performance is maintained by minimising wrinkles and poor sealing. External systems require good vapour permeability to ensure moisture is not trapped within the construction, and this opens up a third possibility. This is to position the air barrier layer within the construction, over the structural sheathing board, but behind the outer layers of the thermal insulation. This increases the protection to the air barrier layers and can help simplify detailing of the membrane. Care must be taken with this method to ensure wind washing through the outer insulation does not occur, for example with use of a vapour permeable jointing tape on the insulation boards. An internal air barrier is only as good as its installation. If all the surface penetrations are not adequately sealed, performance will be compromised. Switches and sockets represent the more obvious paths for air leakage, but there are many others which may be unseen. A huge variety of airtight accessories will be required when using an internal air barrier system. Example of these will include the airtight VCLs, pipe and cable gaskets, junction boxes, extractor fans, switch boxes, light fittings, and sealing tapes, to name a few. These airtight accessories are generally more expensive compared to standard non-airtight versions and take more time, care, and attention to install correctly. There can also be supply chain issues acquiring these products at short notice. In contrast, external systems generally require far fewer components and do not require as complex an installation process, leading to faster completion of the airtight envelope with fewer potential delays and construction errors. The increased speed of achieving airtightness means pressure testing can be carried out earlier, potentially simplifying any remedial action that is required. Combining these benefits in turn allows stricter air design leakage rates to be used, with greater confidence that the lower air leakage rates can be achieved. So now let's consider the benefits of this more reliable air leakage performance. If we can be sure we'll achieve a low rate of air leakage, then we can reduce the design air leakage rate used in our modelling, which means we can reduce our requirements in other areas. In a recent project we were involved in, this improvement in air leakage was traded off against the fabric insulation. In this case, however, the goal was not to reduce the thickness, but to switch from a rigid foam insulation to a less combustible mineral fibre product. Ordinarily, this swap would increase the thickness of the wall assembly significantly, but here, the reduction in emission rate delivered by wrap-tight allowed this switch to happen with almost no additional thickness. This delivers cost savings across the building envelope, as depths of flashings, fixings and various trims can be reduced across the entire facade. So while a high-performance product like the Raptite may appear more expensive at first glance, when we factor in the decisions and trade-offs it enables, it is not as straightforward as it may appear. The final element affecting our building design is moisture management. Controlling and managing the moisture flow in a building is fundamental to the core principles of HAM and also to maintaining the durability of the building envelope, maximising energy efficiency and protecting the health and the safety of the occupants. There are a number of potential moisture sources affecting all building envelopes, the most obvious being the external environment, weather and rain. Most rain screen systems commonly used in high-rise residential and commercial construction are not designed to provide a complete barrier to water ingress. Therefore, the cavity behind should be provided with the provision for drainage to the outside, and care should be taken at design stage so that water may not track into the inner layers. As well as for allowing for the drainage of liquid water, rain screens should be designed to ensure moisture from the interior of the building can escape and that any wetting associated with water ingress through the outer rain screen can dry out. This is typically achieved by fully ventilating the void between the outer cladding panels and the inner leaves of the wall. By ventilating, we ensure moisture vapour from all sources can escape freely to the outside. However, it does also mean that achieving a good airtight seal of the inner leaf is critical to minimise air leakage. A well-designed weather-tight layer is only as good as its durability, and a carefully designed rain screen that cannot resist damage will be limited in its usefulness. Internal moisture sources must also be considered. Achieving an effective and efficient moisture strategy depends on the design being carefully matched to the building's function. The same office design that works for an office may not work well in a sports centre, for example, at least not without significant over-engineering and added costs. Developing a thorough understanding of both how the building as a whole and specific areas within the building will be utilised by its occupants and the corresponding moisture production is key to achieving a robust and cost-effective design. Wet trades such as plastering and screeding and wet materials such as concrete also contribute significant quantities of moisture to the building envelope, which will evaporate to the internal atmosphere in the initial period following the building's completion. This is known as the drying out period. During this period, problems can arise even in buildings that have been well designed to accommodate their moisture loading, as the vapour pressures within the envelope can get significantly higher than normal. Condensation arising from this excess moisture can still cause damage to the building fabric, even if it only occurs for a short period after completion. As well as understanding the sources of moisture, it's important to understand how moisture moves around the building. Vapour diffusion is the movement of vapour molecules through porous materials because of vapour pressure differences. These vapour pressure differences are created because of temperature and humidity differences in the air on either side of the material. Most building materials are unable to stop vapour diffusion completely, and therefore building science uses the term vapour control layers, suggesting that they will control, i.e. slow down, the process, but will not completely prevent the movement of water vapour. Low permeability materials are those which can significantly slow down vapour diffusion. Transfer by convection occurs when airflow acts as a transport mechanism, carrying moisture in or out of buildings. Holes, cracks, penetrations and leaky ductwork may all provide potential pathways for moisture movement. As the moisture passes through the building, it will condense on surfaces with temperatures that are below dew point. Condensation levels will be affected by the difference of temperature between inside and outside, relative humidity and the speed of air movement. Moisture can also be transported by capillary action. This describes the ability of water to travel up through a building or material against the flow of gravity, like for example how water will wick up through a paper towel following the direction of the fibres. Capillary action works best with smaller pores rather than larger holes. For example, the fine pores found in brickwork or concrete provide an excellent mechanism to be used for this wicking action. In order to avoid the occurrence of excessive condensation, which can result in mould growth and damage to the building fabric and/or contents, designers should assess the amount of water vapour likely to be generated within the building and determine the resultant increase in internal vapour pressure above that of external air. They should then consider the physical properties of the construction, separating inside from outside, and how this interacts with the various moisture sources present. Lastly, designers should consider the effects of the external climate, which, being site-related, is beyond direct control, but may be moderated by the building's form and orientation in relation to topography, prevailing winds, sunlight, and overshadowing. Moisture and condensation can lead to mould and bacteria growth, which, if left uncontrolled, can have a significant impact not only on the fabric of the building, but also on the health and safety of its occupants. Assessing heat, air, and moisture. Now we've looked at all the foundation elements of heat, air, and moisture in buildings, we can begin to appreciate how to balance these effectively and how we can ensure this balance is achieved at the design stage. A basic principle here is to ensure that all factors we've already discussed are properly accounted for to ensure that the building envelope performs as intended throughout its life. Calculating the intricacies of heat flows and energy performance can be accounted for using a variety of modelling tools, from simple U-value and S-BIM calculations through to complex BIM models and advanced simulations. The degree of modelling complexity required will vary from one project to the next. Depending on the system used, these models can account for everything from basic insulation levels to complex life cycle assessments and allow comprehensive optimisation of the building design by accounting for all these factors we've discussed. As well as our comprehensive technical support service, here at the Keira Proctor Group we make BIM objects available for a range of our products, enabling easy integration into whatever design workflow you choose. In addition to fully modelling the energy performance, we must also make sure we properly assess how the building design balances moisture. Balance in this context meaning we must ensure that all moisture associated with the building can dry out, and that any moisture accumulation or wetting is balanced and equalled during the life of the building. As with energy modelling, it's important to use the right design tools. Traditional methods of assessment have in the past been based on the Glaser method. We talked a bit about this in last week's webinar on refurbishment, but it's worth reiterating as it's also relevant in a new build context. Developed back in 1958 for use in lightweight buildings, the simplified calculation used by the Glaser method is based on average monthly temperatures, vapour pressure, and steady-state conduction of heat to determine if critical condensation points are reached within 1 year. The limitation of this approach is that Glaser assumes vapour moves only one way, from inside to outside. It also completely omits the key feature of driving rain from its calculations, does not measure absorption or porosity, and therefore fails to identify potential risk attributed to the aspect of moisture storage. While this basic model is acceptable in some cases and useful for providing a rough guide to avoiding the worst and most obvious problems, a proper assessment of the wetting and drying balance of structures requires a more substantial approach. Outlined in the EN 15026 standard, this enhanced approach dynamically predicts moisture movement and storage as well as condensation for each location, taking into account climate effects such as driving rain and solar gains. The most common software used to assess structure via this method is known as WUFI. Using this modelling means the designer can achieve a minute-by-minute prediction over a given period of years, which provides invaluable when assessing the correct position for high-performance vapour control and vapour-permeable membranes to ensure a healthy building fabric. We can see from the example here that the Glaser method calculation simply shows that no condensation risks are predicted within the construction. A more comprehensive assessment with WUFI shows the rate at which construction moisture is drying out from the wall. We can also examine the differences between the placement and specification of various components within the wall. Here we can see the difference in drying out periods between internal and external placements of insulation. Placing insulation externally leads to a much faster reduction in the moisture contents in the masonry compared to placing it internally. So although there's no problems predicted using the Glaser method, WUFI clearly shows a better hygrothermal balance is achieved with external insulation over a longer period of time. The latest code of practice for the control of condensation, BS 5250/2011, incorporating the 2016 amendments, details when it is more appropriate to use EN 15026 or WUFI software and when the simpler Glaser method is acceptable for various types of building element. It is however clear that for more complex scale structures, a more dynamic and extensive approach enabled by using the latest software and improved computing power is not only desirable but more widely achievable than ever. Between WUFI moisture assessment and the more complex energy modelling enabled by modern BIM software, It's now possible to model the balance of heat, air and moisture accurately, and hence to design and specify with much finer tolerances. This helps ensure a cost-effective and robust building that remains fit for purpose for many years. So in conclusion, I hope we've illustrated a few of the factors we consider when looking at optimising building design, and we'll now move on to the Q&A session. Hi everyone, welcome to our third lockdown webinar. Thank you very much to Peter, who reminded us to mute our microphones. I'm not sure who it was, it might have been me, if so apologise. All sorted now though. So thank you for joining us, a beautiful day today. So first of all, I hope you're all keeping well and that you can enjoy some sunshine later on. And it would be nice to get out and about in the garden, I think. I will just go over a couple of housekeeping and what's next, and then I'll introduce the team here. So you will be able to get a personalised CPD certificate for the webinar today if you go to proctorgroup.com/webinar-certification. We love getting your feedback. So as usual, there will be an email coming out to you which has a survey and also a replay of the webinar. So two things, please circulate the replay of the webinar to any colleagues or people in the industry who may find of interest. And with the surveys, I personally read every single one. Any feedback you have, positive or negative, and we do use it and sort of modify the future webinars. So we really love feedback, so please spread them out. We're continuing these weekly webinars every Friday, so we're very committed to that. Next week at the same time, 10 a.m, we have impact and airborne sound solutions for floors. And again, we'll have the live Q&A afterwards. So if you can join us, please do. And I think that's it for now. Questions can be put in the YouTube channel. You can DM us on Twitter. We've already had quite a number through email to webinar@proctorgroup.com. So please send more through and bear with me while I'm asking the questions because they do come from quite a few different platforms. So just bear with me on that. Joining us today, back by popular demand, we have Sue Menmuir. Don't let looks deceive you. She's been working for us for 27 years in our technical team. Mark Lambourne. Morning, Mark. Sue's up based in Bulgaria. She lives about 40 minutes from myself in the office. And Mark is based in Arlington. And he's had 34 years in the construction industry, believe it or not. And he recently rejoined Proctor Group after quite a long stint with insulation and manufacturers. So we managed to coax him back, which is fantastic. And James Brackenridge-Jones is based in Eastbourne. He's a recent member of our team, has a huge amount of specification background and covers the London area for the specification. So I don't think I've forgotten anything. I'll just start with the questions, and as I say, please keep them coming on the various channels I explained earlier. So James, if we can start with you, one's come through from email from John. Where facade system and corporates helping hand brackets, is there a requirement for a thermal break?
Yes, I mean, as an industry standard, we would always assume that there is a requirement for a thermal break to be installed behind the bracket. It's taken into consideration when we're carrying out our calculations. The discussion will always be had with the supplier, the specifier of the project, in order to fully understand the build-up initially and the products involved to make sure the system will work for the lifetime of the property. Indeed, through utilising our WUFI analysis, we'll make sure that there's no surface or interstitial condensation risk. So having that thermal break will be required. But obviously, if there's the ability to negate that thermal break and the building insurer and the architect and the client are happy with that, then we can proceed. But as a standard rule of thumb, we'll do the belt and braces scenario first, which is obviously integrating the thermal break into that area.
Okay, great. Sue, if I can just ask one from Peter that was on the YouTube channel. He's curious about healthy office and residential design. How do you calculate heat and perspiration, so moisture from a person and heat from a workstation, for example? What are the optimal moisture and heat conditions?
We take guidance from BS 5250, which gives recommended vapor levels. So that would be taken into consideration when you're doing a condensation risk analysis. If you're doing WUFI calculations, they also have inbuilt levels, moisture levels that you can take as well for different scenarios.
Okay, that's great. Thank you very much. Sue, while we've got you, one from Oren through, again, the webinar do you always need a cavity when using a reflective membrane?
Yes, to gain the thermal benefit. Earlier in the webinar, we spoke about radiation and how heat travels, so heat transfer by radiation. With a low emissivity membrane, that obviously is less able to allow the heat to actually transfer through. So that's where you gain the thermal benefit. The other advantage is also if you have that cavity, there's less chance of your membrane being punctured, being damaged. So it remains, like its integrity remains intact.
Okay, great, thank you. Mark, I've got two wrap type ones, well there's more actually, but two application ones on wrap type. One from Ian Kirkhope. In respect to the positioning of the wrap type product, your comment about foil taping joints of the external insulation to prevent wind wash would suggest that you're referring to a foil face insulation. What are your views on the central positioning of the wrap type product if the external insulation was, say, a rock wool slab? Mark, is that one you can do?
Yeah. Right, morning everyone. Yeah, and certainly with regard and the reference really within the webinar to taping the joints of insulation boards is typically, I guess, right in the early days of wrap type. So whilst we sell and take to market the wrap type membrane at 1.5 meters wide, we also do a range of tapes ranging from 75, 100 and 150 as standard, but they can be sort of, we can manufacture tapes at any particular width you require. And the taping of joints was really with plastic foam insulation. So the contractor has got a sheathing board, perhaps a concrete frame building. There was a sheathing board fixed into place. And then they would have used a mechanically fixed breathable membrane and then applied the plastic foam insulation over the top and mechanically fixed that through. And then to seal the joints to prevent moisture ingress during the construction phase, etc., they put tape, wrap type tape, to seal the board joints. But typically on the projects that we're involved in these days with high rise and sort of mixed use projects, the wrap type membrane is adhered to the face of the sheathing board, and that wraps the building, provides an airtight self-adhered layer, and then rock or duo slab or similar type of mineral wool products are then installed over the top. And typically there'll be, if it's a brick outer leaf, there'll be an Ancon rail system fixed through, and then the clips are tied into that, and then your brick outer leaf.
Great, thank you. And another question in from James: does a construction using wrap tight require a vapor control layer? Mark, if I can.
Yeah. In our experience, sort of frame buildings, whether that be concrete frame or steel frame, such as those in high-rise residential mixed use with external insulation, are less likely to require a vapor control layer. So typically the facade through wall construction includes insulation within the SFS and also externally in front of the sheathing board, as Ian suggested earlier. And really it's the balance of the insulation which determine if there's a need for a vapor control layer. And it really depends, I guess, on the location, the type and the thickness of insulation. So when we do our hydrothermal assessments, the WUFI calculations, we'll take into account the geographical location of the project, the vapor load, as Sue was talking about earlier, the use of the building, and that will give us the definitive answer as to whether a VCL is or isn't required.
Great, okay. And while we're on James, we might as well ask the other question. It's great that these are coming through, so thank you. So I would usually request a U-value calculation. Sue, perhaps you can take this question. I would usually request a U-value calculation from the insulation manufacturer. What information would you require for a WUFI calculation to provide a more detailed hydrothermal assessment?
Okay. I say it's a more detailed assessment, so we do need a lot more information. We will still need the typical things that you would need for a condensation risk, i.e. what the construction build-up actually is, what the products are used. But we'd also need to know the vapor resistance of the product, thermal conductivity, the orientation of the building, of the element of the building, the height. That all has an effect. We can calculate it over different calculation periods. So typically it would be 10 years, but we could do 5 years, 20 years, etc. and also the internal climate conditions as well, which like we would need as well to get a full assessment.
Okay, good. James, we have one here. There's quite a lot of raptite-oriented ones, which is great. From Jim, how is the raptite terminated around window reveals and door thresholds?
Okay. Due to the self-adhered nature of the raptite product and its ability to adhere to multiple substrates, it's actually turned into the window reveals and door thresholds, or basically any opening on the external facade. It's then lapped onto the internal surface, so there's no problem going from the sheathing board to the metal, concrete or timber frame. Obviously the transition between the different materials due to the product and the adhesion of it, it can adhere to multiple different products and do the junctions between them. Regarding the corners of the openings, which is obviously the devil is always in the detail, we have prefabricated corners which are produced in our factory in Blairgowrie. Obviously, from my point of view, I work very closely with the specifier in order to get the window and door schedule program put together, so that we can make sure that those depths of reveals, those depths of thresholds are taken into consideration prior to being built. It just ends up securing the process of specification. But then again, from that point of view, we'd work with the contractor to make sure that as designed is as built, as all we know changes somewhat when it gets to being on site. And what these do is ensure the airtight, watertight line in order to aid the ease of install and indeed allow the the vapor permeability of the product to negate any condensation risk in that area. Ultimately, what we're after is to provide us with your details of your project, and we'll carry out CAD details of those specific detailed areas, even from a penetration of a vent pipe coming through the external wall. We'll carry out those CAD details. We've got the installation guidelines to assist. We'll be on site if you need us to assist as well. We'll be there as much or as little as we need to.
Okay, great. And Sue, do we carry out psi calculations? Carol's asked.
We don't carry out psi values. Psi values are used to calculate like repeated thermal bridging. So they are used in SAP calculations, and those values would then be inputted into your SAP, which would then have an overall effect on your emissions.
Okay, that's good. Thank you very much. Mark, here's another one from a Carol actually. Can you recommend a membrane which would protect the insulation layer and structure from the elements, including moisture, heat and UV, where the facade features open rain screen?
Yes, we have a product called Facade Shield UV, which is a non-woven, airtight, breathable membrane. It's dark in colour, so it provides a shadow sort of appearance behind the open jointed rain screen facades. In fact, we have, for people if they want a copy, we've got the Ham Principles brochure. And despite the fact Mrs. Lambourne is always telling me to tidy my office, I can normally lay my hands on things fairly quickly. And you can probably just see there's an example here of the Facade Shield UV. So it's dark in colour, so it provides that shadow gap detail. And it really offers high levels of water resistance, so it's a class W1. And during the construction phase, may be left fully exposed for up to 12 months. So if you consider a typical wall membrane or roof membrane, normally about 3 months is the maximum exposure. So this will be available fully exposed for up to 12 months. But once the facade's in place, where you've got a facade with open joints up to 50 millimetres wide, it will remain in position and perform for the lifetime of the building. Now, it comes with a UV-resistant black sort of tape as well to detail all the laps and assist with their tightness. And depending on the substrate it's going on, it can perform up to Class B. So Class B S2 D0.
Good, okay. Quite a similar question from James. I think it's a more generic question regarding membranes, not particularly for open facade, but the typical lifespan of membrane and tapes. Are the adhesives stable and don't degrade? Are they fully resistant to weather exposure during construction?
Yeah, certainly the raptite. With regard to roofing membranes, it can be difficult to install tapes, particularly where you've got a drape. And certainly with some of the lighter weight membranes, that can be a bit of an issue if you're on a roof with a drape and trying to press down some of these membranes that require the laps to be taped. But certainly with the products that we sort of take to market, they have been tested for long-term exposure and that type of thing. So there's no issue, particularly with the wrap-tight membrane or the wrap-tight tapes. And the same with the Facade Shield UV tape.
Okay, fantastic. James, I have a thermal bridge. This is from Jolene. Nice name. I have a thermal bridge caused by steel framing. How do I deal with this, and won't mechanical fixings breach this?
In regards to the steel framing side of things, then yes, I mean, obviously to negate the cold bridge through that steel frame, you need to block that cold bridge with an insulant. We have insulation, which is a very high performing. We have an A2 version, or we have a Class C version, depending upon the constraints of the project. Obviously what we push for, especially in this day and age, is to utilize the A2 product. But utilizing a 10 millimeter, we've got cold bridging strips which can be provided, or you can use a full sheet of the material in order to mechanically fix back to that steel frame in order to get the cold bridge through that axis. Obviously, taking into consideration what fixings you're using and making sure that they're thermally broken as well.
Okay, great. So do you have anything to add?
Sorry, ultimately we need to know what the project details itself, and then obviously we can put a CAD detail together for you to assist in negating that cold bridge.
Sure, great. So do you have anything to add to that one? I probably should have directed it at you, but
no,
well, James, thanks.
James has just answered that fully.
Good.
Well, let's stick with James then. Callum has asked, how do you take into consideration moisture content in cast on-site concrete as opposed to precast?
Okay. Again, devil in the detail. The product will go on as well as you look after what it goes on to. It can be adhered to damp substrates, again, because of the nature of the product and because it's vapor permeable. Even if it does go onto a damp substrate, that vapor drive will still occur through it. So the concrete will still dry out naturally, and indeed a lot quicker than if you're utilizing a EPDM of any description. But what we'd always stipulate is the drier the better, obviously, especially on a new cast. And then obviously with a new cast, you've got the latents that start coming out of the product as it starts curing. So making sure that they've been removed in regards to dust or anything on that sort of line, any cement latents that come out. If the product is precast, then obviously to make sure that that surface, once delivered to site, it's cleared of any sort of loose material or dust, any excessive dust or loose material, in order to make sure there's a good bond. If there's any lifting eyes that have been put onto those planks that have been sealed up, obviously you get the sort of the concave areas of those lifting eyes. Once the lifting eyes have been taken out, then to screed over or cement over those, leave it a couple of days or a week in order to get the moisture out of those, and then the product can go over. But ultimately, the bond will be as good as the material that it goes onto. So you can utilize damp meters to obviously check if the surface is dry or how damp it actually is. And if you've got any questions, if you use the damp meter and there is damp there, please make a phone call beforehand, or indeed try a small patch area to see if the product is adhering properly.
Okay, fantastic. I think I have 3 more via email, and then we'll come back to the YouTube if I can just get through these ones. Mark, does Wrap-Tight improve the U value?
I guess when Sue and Callum in our technical team, when they do our U value calculations or using the glazing method or the Woofy calculation, which also produces a U value calculation within it, we don't count Wrap-Tight as having any thermal properties within a typical wall build-up. But that said, it will improve the target emissions rate within SAC calculations, so the building will be more energy efficient. So if we can get involved in the project at an early stage and incorporate that into the design, we can maintain the same sort of target emission rates, but by reducing the insulation thickness, the improvement in air tightness would sort of offset the difference. So whilst there's no thermal properties, we can demonstrate through a SAC calc that there is an improvement by using the Wrap-Tight.
Okay, great. Another one, Mark. We've traditionally specified and installed vapor control layers to achieve air tightness. What cost savings, if any, can be achieved on using an external membrane system?
Well, the obvious one is of course taking out, providing the hydrothermal assessment report demonstrates so. We can initially take out the traditional VCL that's been used to provide the air tightness, obviously. So with wrap-tight being self-adhered, the membrane negates the need for, certainly for mechanical fixings and tapes. We spoke just about the possibility of reducing the insulation thickness. So that has a knock-on effect with regard to short helping and brackets, fixings. So the fixings to hold, say, the Ancon rail system in place over the top of the Rockall Duo slab. By having a fully self-adhered membrane, we can detail the wrap-tight across the concrete frame and columns. So that can mean less EPDM has been used. So we can reduce the fire load on the building, and certainly there's less cost there for having to prime and install an EPDM type membrane. And as the building is made, I guess, watertight in early stage, and provided you've got your windows in, then all the internal trades can begin. And we've certainly got evidence of projects where they've come in 3 to 4 weeks early on the build program. And one of the biggest cost savings, of course, is security these days. So if you can reduce the security costs on a project by bringing it in 2, 3, 4 weeks early, that makes a huge saving, which I guess ordinarily wouldn't be considered when you're looking at cost comparisons on breathable membranes.
Fantastic. I'm not aware this is something we would do, but we've had a question in from Stephen. Maybe you can help him anyway with this question. Can you recommend any product for a cold flat roof to avoid condensation problems?
Cold flat roof, okay. Flat roof construction in general has a high risk of condensation occurring anyway. Ideally, if you are doing a flat roof, it's preferable to do a warm flat roof where the insulation sits above the structural deck. For a cold flat roof, we would incorporate a vapor control layer at ceiling level, obviously, and you would then have to ventilate a cold flat roof anyway, which also helps with the reduction in condensation. Okay. But typically, you always get a condensation risk in flat roofs.
Great. That's something we could do in-house. Although most of our products are kind of lend themselves to wall and pitched roofing, but we could still help with that.
We can still provide vapor control layers for flat roof constructions.
Okay, good. It's quite a long question, so if you don't want to answer it now, Sue, that's fine. Perhaps we can go back via email, but I'll ask it anyway, just for the benefits of others on the webinar. This is from Dante. What effect, if any, does moisture evaporation have on the R value of a low emissivity cavity? So considering where low emissivity cavity is placed on the cold side of the construction, so typical scenario, timber frame construction with 100 mil block cladding, 50 mil cavity, and a foil breather membrane on the face of the timber kit, where the foil membrane may be subjected to the effects of condensation or wind-driven rain, etc.
The moisture won't actually have an effect on the emissivity of the product. Really, the only way the emissivity of the product can be affected is if it gets damaged, for example. Our reflector shield, which is our low emissivity breather membrane that we would use in that situation, is designed, that's where it's designed, exactly to be used on the cold side within the cavity. So it's generally the only performance reduction you would get is if you were using it behind a well ventilated cavity, such as behind timber cladding or like a render board, for example. Okay, that would be an issue.
Good. Okay, thanks for that, Sue. James, I think this is the last one we have on email, unless any others are coming in, and I will have a look and then come back to the YouTube questions. So James, where there is a requirement for a vapor control layer within high-rise residential projects, do you have any fire-related products we can specify? Quite topical, this obviously at the moment.
Yes, I mean, obviously there's, again, the topic of it. Obviously the topic predominantly is from the external facade point of view, but what we're obviously from a manufacturer's point of view, and not necessarily conforming to building regs, but trying to enhance building regs. What we're doing is we've released 2 products, one which is called FR200, the other one which is ProCheck A2. The FR product is a Class B S1D0, which obviously exceeds the requirements in building regs in regards to facade membranes. But obviously some people will say, well, it's an internal system, it's not part of the external facade, so therefore it doesn't need to conform. But obviously from our point of view, what we're trying to do is do the best we can do with what we have. And therefore we've enhanced obviously what we've got with that FR200, and we've released the ProCheck A2, which is an A2 S1D0 VCL. Its composition comprises of a glass fiber backing with a pure aluminium foil and clear lacquer coating. This composition affords the membranes its Class 2 performance, as well as giving it a high degree of vapor controlling properties. Again, as Sue mentioned earlier, having that 19 mil service void allows for the lack of penetration. So therefore the emissivity value is also improved as well. So yes, if you've got that and you want to progress and sort of do much better than just like we do with the thermal side of things in regards to insulation, rather than conforming to 0.2 or 0.3, you want to go for your 0.16s, you want to go for your 0.14s, then that's what we're here to do. We're here to push the industry forward and make sure that they're not sort of sitting on the back foot, just going for the standard qualifications, classifications that can be achieved with products in this day.
Okay. Mark, perhaps you could answer Gordon's question, which is on the YouTube chat. How compatible are the membranes with others, such as EPDM, when sealing around openings?
There's 2 approaches really with the wrap-tight system. As James said earlier, when we dress the membrane through, so if we take it over a window opening, if you imagine it being installed onto a sheathing board and across a window opening, you can take the membrane across, cut with a knife across through the membrane, and then dress that membrane through the window openings. We have some preformed corners, and it's at that point then the guys will install the EPDM onto the wrap-tight to provide the waterproof element, etc. The other approach is to put the EPDM membrane and waterproofing around the window first, and then take the wrap-tight up to it. So there's really 2 approaches, and it really depends on the design team which way they want to take to move that forward, really.
Okay. And Sue, if I can come back to you, there's a sort of general, what services does the Proctor Group offer to designers, and a more specific question from Peter. So if you can answer the more sort of general services we offer, and also take his question at the same time, that we mentioned about prefabricated corner CAD details. Do we provide any Revit BIM library of your specialised details and U-values, etc.?
Yeah, yes, we do. We provide a wide range of services, such as U-value calculations, condensation risk analysis. We also have a library of BIM objects on the website available for download. We do obviously call support, email support, and online support, on-site support, sorry. So we do have a wide range of services that we can offer.
Okay, fantastic. A couple of last ones here. Mark, Peter's asked, you mentioned about, I've just asked that one, so let me start again, sorry about this. Designworks have asked, I've had structural warranty problems with breather membranes behind the external overlap of insulation. Reason being given the PIR not designed to be exposed to wetting, so that makes sense. Is that one you can answer, Mark?
Yeah, sure. I guess most PIR products have some kind of facing on them. So typically that will be a foil face. As I mentioned earlier during the Q&A session, there's a situation where contractors are using wrap-tight tape, so they're fully self-adhered, vapor permeable but airtight tape over the joints of the board. So if you're fixing, sort of mechanically fixing, or whatever it may be, the insulation to the face of a membrane, you can use the tape to seal those board joints up, and that will prevent any moisture going through, but still allow the system to breathe, as it were.
Okay. A couple of last question, I believe. Well, Alan, first of all, I hope you got our heat, air, and moisture management brochure from our website. We have a lot of literature available on our website. So if you go to proctorgroup.com, you should be able to download either by product or by sector what you require, or email us and we'll happily send it across to you. Rory's asked, do we have any plans on making the wrap type reflective to allow the joining cavity to be classed as low emissivity? That's a good point, actually. It is something that our R&D team have discussed, and we've been doing trials in-house. So we don't have anything commercialized at present, but if we do, you know, we'll keep you up to date on that. Okay, I think I've come to the end of all the questions. So if I can just quickly summarize, don't think I've missed any. If I have, I apologize. As I say, there's a lot of different platforms where these questions are coming through. And I did say on the last webinar, I'm not the best multitasker because they're coming out from Twitter and all these different social media places. So if we have missed any, we will come back to you via email. So please contact us at reception@proctorgroup.com or webinar@proctorgroup.com. So thank you for so many of you staying on for our team for the Q&As. Often we find this the most beneficial part for the business because we can understand the type of questions that designers and specifiers have. We can answer them. We then take this and we have a meeting afterwards, and we can go and adjust our, you know, literature and information afterwards to make sure that the relevant information is there for people to find when we're not having these webinars. So it's really, really good. So thank you for attending. You're adding a lot of benefit to us, and likewise we hope that we're doing something educational and helpful for you. Again, there's a personalised CPD certificate available if you go to proctorgroup.com/webinar-certification. You can now sign up for next week's webinar. So it's already live on our website, which is proctorgroup.com/webinar. It is on acoustics next week, so impact and airborne sound solutions for floors. Now, as a business, we've been in acoustics for many years, over 20 years. We have a lot of experience in that sector. And predominantly, we're now known for breathable and airtight and vapor control membranes, but it is something that we know a lot about, and we still do a lot in as a business. So please join us, and we'd be happy to share that with you. I think that's it. You will receive an email afterwards when you have the survey questions which I spoke about earlier, and a chance to replay the webinar or to circulate the webinar. So if I can just thank the team, well, first of all, the marketing team that are not in front of the cameras here, but they've done such a great job producing these every week. So well done, guys. I know you're listening somewhere. And thank you very much to Sue, James and Mark who answered the questions. Great today. It's really hard to answer these questions on the spot. So each time after these webinars, it's fantastic to go away and just remember how knowledgeable we are individually, and our team is being able to help people. So fantastic. And enjoy your Friday and the weekend. I think we're set for a good weekend, but stay in and stay safe, and have a lovely time with your families. And hopefully we will see you next Friday. Thanks, everyone.
Thank you.
Bye.